Hello everyone, welcome to the course Network Theory. This is Dr. Satyavani Bandela, Assistant Professor, SR University, Warangal, Telangana. So today we are going to discuss the lesson number 4, that is Kirchhoff's voltage law. Let's briefly discuss about the previous courses, whatever we have discussed in lecture number 1, lesson number 1, Introduction to Electrical Elements. In that we discussed briefly about electrical types of electrical network elements, classification based on the direction of current, based on the magnitude of voltage source and current source, dependent parameter, independent parameters, and passive elements like resistor, inductor, capacitor, their symbols, units, and their properties. And in lesson number 2 we discussed Ohm's law. Again I am repeating the statement of Ohm's law is provided at constant temperature, current to the conductor is directly proportional to applied voltage. Now in that we see the equation, finally derived equation, V equals to IR. So this is provided at constant temperature. Along with this Ohm's law, we discussed power, electrical power, which is a product of voltage and current, and electrical energy, which is a product of power and time, and the units also we discussed. Then next in lecture number 3, we discussed Kirchhoff's current law. So this Kirchhoff's current law, KCL, statement, that is algebraic sum of currents at node equals to 0. And the definition of node we have taken in any network, the point at which two or more branches are connected together, that point is known as node or junction. At node or junction we are going to apply this Kirchhoff's current law, and that is algebraic sum of current at node equals to 0. So these three topics we discussed earlier. Now today we are going to discuss Kirchhoff's voltage law with example problems. Now, so according to Kirchhoff's voltage law, this already we discussed that KVL and KCL statements, where this Kirchhoff's voltage law is based on the law of conservation of energy, and where the Kirchhoff's current law is based on the law of conservation of charge. Okay. Now here I am giving the overall definition of KVL and KCL again, and KVL is algebraic sum of voltages, in closed circuit, equals to 0. Okay. And KCL is algebraic sum of current at node or junction, equals to 0. Now let us take how to apply, what are the properties while applying Kirchhoff's voltage law in next slide. Now here again I am telling the statement, algebraic sum of voltages around a closed loop at any instant equals to 0, and this is the equation, Vn algebraic sum of voltages in closed circuit equals to 0. But what is meant by algebraic sum? See here, the algebraic sum depending on the polarities of the voltage and the drop of the voltage across each and every element. Now see how to take those drops, how to add the voltages in a closed circuit, that we will see here. If the drop in the potential is with the direction, if we are moving from positive polarity to negative polarity through any element is taken as a negative voltage, and the rise in potential, that is from negative polarity to positive polarity, is taken as positive. Just see the polarities. When we are crossing any element from negative to positive, here we have to take positive, and if we are crossing any element from positive to negative, then we have to take negative voltage. Okay, let us take one simple example circuit. In that we will see how to apply this Kirchhoff's voltage law. So this is the example circuit that I am taking, and here in this network, now look at the elements. The first element is Vs, voltage source, and where the voltage source polarities are given minus plus like this, and magnitude of this voltage source is Vs. And then next after this another element, and that is Z1. It is given voltage across Z1 is already represented with plus minus voltage V1, and voltage across this Z2 element with the polarity plus minus, and the voltage is V2, and the third element Z3 and voltage across this is V3. Now here I am applying KVL. Start from here in our direction. The first element we are crossing from minus to plus, so that's why it is plus. What is the magnitude of this voltage? Vs. Then next after this we are crossing the voltage V1, which already existed across Z1, and we are crossing from plus to minus polarity, that's why it is minus V1. So after this again the second voltage V2, we are crossing this from plus to minus, that's why it is again minus V2. And similarly the voltage V3 from plus to minus, that's why it is minus V3. So after this, is there any other element? No. So there are 4 elements, so you will get 4 voltages: Vs, V1, V2, V3. Where for Vs it is positive, and for remaining all 3 voltages minus, because we are crossing all these voltages from positive to negative, so that's why they are minus. Now KVL is algebraic sum of these voltages in closed circuit equals to 0. Okay, so means finally we can write the source voltage Vs equals to voltage across Z1, that is V1, plus voltage across Z2, that is V2, plus voltage across Z3, that is V3. So like this we have to apply KVL in the network if voltages with polarities are given. Now let us replace these impedances with resistance by considering the direction of current. Now how to apply KVL in case of the direction of current and the resistances are provided. Now we will take one more example circuit. Now here I am taking there are one example circuit with voltage sources numbers 5 and 5 voltage source and 2 voltage source with 3 different resistors 5, 10 ohm and 15 ohm. And here the question is find the current I and voltage drop across 15 ohm resistance. So now let us take the voltage across this 5 ohm is V1, and voltage across 10 ohm is V2, and voltage across 15 ohm is V3. Okay. Now when the direction of current is taken, because it is already represented like this, okay, means when the direction of current is taken like this, when current is flowing through this resistance, it is taken as from higher potential to lower potential, or from plus to minus the direction of current from through resistive element, like this we have to take. Okay. And now here also the direction of current is like this, so that you have to take the polarity across this element plus minus. Okay. Now the voltage source, it is already existed voltage source with polarity plus minus. Okay. So we should not take our own polarity directions. Okay. And voltage across this resistance V3 we are representing, but how to take the polarity? See, the direction of current is like this. So entering to the resistance is plus and leaving with minus. The same way like 5 ohm, entering plus and leaving minus. Current entering to 10 ohm with positive and leaving with minus. This is also resistance, that's why entering with the plus and leaving with minus. Like first we have taken the polarities across voltage across each and every resistance. Now here I am applying the KVL. Now see the KVL application, KVL. Okay. Now what is our first element? 5 volts. Okay. So this 5 volt in our direction we are crossing from minus to plus. So minus to plus means plus 5. Okay. The next V1 we are crossing with plus to minus. Is it right? From plus to minus means it is minus V1. The next, what about this V2? Plus 2 minus we are crossing, that's why it is minus V2. Then the third element is 2 voltage. Now we are crossing this plus 2 minus, that's why it is also minus, the magnitude of voltage source is 2. Okay, so we are crossing plus 2 minus, that's why it is taken as 2 volts. Then after this plus 2 minus again, so minus V3. Is there any other element? No. That's it. So like we covered all 5 elements, 1, 2, this is second, third, fourth, fifth. Algebraic sum of all 4 voltages equals to 0 according to KVL. Okay. Now here I don't know what is the current. Let us take unknown current I, because we have to find out this current. So we assume this is the current that is flowing. Okay. Now here I am writing as it is 5 minus. What is V1 actually? Let me write V1 with a different color. So what is V1 here? V1 is the voltage drop across which resistance? 5 ohm resistance. So according to Ohm's law, so voltage across this resistance V is I into R. So what is the current that is flowing through 5 ohm resistance? I is the current that is flowing through 5. Means you have to write I into 5. Okay. Then similarly what is V2? V2 is the voltage drop across 10. Then what is the current? Same I is flowing through this 10. So that's why what is V2? It is I into 10. Then similarly, how can I write V3? V3 is the same current because it is a single loop. Okay, there is no different current. So common current flows throughout the circuit. So here also the current is capital I, and V3 is I into 15. I into 15. Okay, now substitute these values here. 5 minus, let me take the right color, 5 minus I into 5 minus V2 is I into 10. Let me take in bracket minus 2 minus I into 15 equals to 0. Let me write this 5 also in bracket. Now 5 minus, this is how much? Minus 5 minus 10 minus 15 minus 15 minus 15 minus 30. Okay, so minus, let me write first number, then next I, minus 30I and minus 2 equals to 0. Okay, now 5 minus 2, it is 3 equals to 30I, and what is the current? I equals to 3 by 30, it is 1 by 10, it is 0.1 ampere. Okay, so how much current? What is the current magnitude in this network? Current I we got 0.1 ampere. But what is the question? Now after finding this current, it is asked that what is the voltage across 15 ohm resistance. So what is the voltage across 15 ohm resistance? That is V3. So what is V3? I into 15. So voltage across 15 ohm, that is V3, equals to I into 15, where I is 0.1 into 15. How much it is? 1.5 volt. That's it. So like this you have to solve the network. So here I am taking another circuit with the different elements. Let me draw that network with voltage source symbol like this, positive and negative, and here one resistance. Here I am taking another resistor, and here I am taking the voltage and one more resistor, and at the end this is one more resistor and minus plus. Okay, so only single circuit I am taking, and take the number. This voltage source magnitude is 10 volt, and here it is 2 volt, and this is 3 volt. Okay, now let us take the resistance values with the different number. 5 ohm resistance, 2 ohm resistor, 3 ohm resistance, and 10. Okay, now here the question is apply KVL and determine voltage across each resistor and power across each element. So first see, the first we will apply, read the question properly, and what is the question that is given. So first apply KVL and determine voltage across each resistance. If you want to get the voltage, so according to Ohm's law we have to take V equals to final equation, V equals to IR. Voltage across resistance is a product of current and resistance. So without current we cannot determine the voltage. That's why resistor values are given. First we have to find out the current. Here I am taking the direction of current like this with I. I am moving in clockwise direction. Okay. Now see, here I am not taking any polarities. First see how to identify the polarity of the voltage source. See here, this is the short length and it must be minus, and this is plus polarity across the voltage source. And here this is short terminal minus, it is represented like this, DC voltage source, and this is plus. And here we have one more voltage source, and short length representation is negative polarity plate, and this is positive polarity plate. Okay, so first let me write the voltages, later we will write voltage across resistances. See here, minus to plus. Here I am writing first all voltages. Let me take another color. So first voltage source is 10, so that is plus 10. Okay, then next, voltage drop across resistances are, just now we discussed with this direction, this is minus 5 into I. Minus 5I. Now with this direction, again what is the next element? 2 ohm resistance. What is the voltage drop? Here I am not taking again V1, V2, V3. So direct we write voltage across resistances as a product of current and resistance. Now voltage across this 2 ohm resistance is I into 2 or 2I. So, but it is negative drop minus 2I. Okay. Then next, now this is the voltage source, and here the polarity is plus minus. It is already given. So that's why when we are crossing plus to minus, it must be taken as minus. What is the magnitude of the voltage source? 2. Voltage itself 2, that's why here I am writing 2. Then next, after this 2 voltage source, what is the element? 3 ohm resistance. What is the voltage drop across this 3? I into 3 means or 3I minus 3I. Voltage drop across 3 ohm resistance is 3I. Then what is after this? We have one voltage source, and that voltage source magnitude is 3, and we are crossing this from minus to plus. When we are crossing from minus to plus, it must be taken as plus. And what is the magnitude of this voltage? 3 is the magnitude of this voltage source. Is it right? Then after this, we have 10 ohm resistance, IR drop. Okay, voltage across 10 is I into 10 or 10I, and drop is taken as minus 10I. So after this 10 ohm, do you have any other element? No, because already we started from here, we covered all the elements and we came back to the initial position. Okay, so how many elements? 1, 2, 3, 4, 5, 6, 7. 7 elements means you will get 7 voltages. Now look at this here, 1, 2, 3, 4, 5, 6, 7. So 7 elements are there, 7 voltages equals to algebraic sum of 7 element voltages equals to 0. Now from this, now simplify this, 10 minus 2 plus 3. So it is 13 minus 2, it is 11. Okay. This is 11, and here minus 5 minus 2 minus 7 minus 10 and minus 20. So minus 20I equals to 0. So from this we can write current magnitude I equals to how much? 11 by 20 ampere. Okay. Then next, so after this voltage, so to find out voltage across each element, first we got current throughout the network, common current. Okay, that is 11 by 20. Now see, 1 by 1 element. The first, here I am writing the first element, voltage across. So already this is the voltage source 10 volts. So no need to calculate, because already magnitude of this voltage source itself 10. But what is voltage across 5 ohm? Here we have to calculate. So voltage across, now let me write like this, voltage across suffix I am taking 5 ohm. Voltage across 5 ohm is I into 5. So that is, what is I? 11 by 20 into 5. Okay. Now we'll calculate that. Now this value, here it is 1155 by 20, it is 2.75 voltage. Okay. So this is the voltage drop across 5 ohm resistor. Okay. Then next, what is the voltage across next element? 2. Voltage across 2, it is I into 2. So 11 by 20 into 2, it is 1.1. Is it right? It is 11 by 10, it is 1.1 volt. Similarly, how to write voltage across 3 ohm resistance? I into 3, and that is 11 by 20 is your current, and the resistance value, here it is it is 33 by 20, it is 1.65. Then next here I am writing the remaining element voltage, that is 10 ohm resistance. Here voltage across this I into 10, where I is 11 by 20 into 10. So this is 5.5. Okay, so this is voltage across this V you have to take. So all these are voltages across each and every element, but it's not only limited to voltage. It is asked that what is the power. So after Ohm's law we studied power equation. So power can be represented in three forms, that is power equation. Let me write power equation. P equals to, in terms of voltage and current, it is V into I. In terms of current and resistance, it is I square R, or in terms of voltage, it is V square by R. So there are three different forms of power equations, and see the data, whatever the data which is available, based on that data you have to select particular equation, whether this is Vi, I square or V square by R. Now let us calculate power across every element, whether that is power delivered by the voltage source or power consumed by resistance. For power calculation, here I am taking very simple circuit diagram, and with only two element voltage sources and two resistors. See here, now here I am representing voltage source with the circuit diagram, so that you should not get confused, because either voltage can be represented like this, DC voltage source, or like this. There are two different forms of representation of this voltage source, and here I am taking only two voltage sources. Let us take one more resistor, and this is 15 voltage source, and here I am taking plus minus 5 volts, and this is take 2 ohm resistance, and here it is 1 ohm resistance. Let us take how much it is. Let us take one more 2 ohm resistor. Okay, no, just take 3 so that it will be very simple. Okay, and let us short circuit, so there is no element here. I am taking only two resistors and 2 voltage source, so that we can finish this problem early. So now here again the direction of current I am taking like this, and now apply KVL. So when I apply KVL, now minus to plus, this is plus 15 volt. The next element is resistance. The drop across the resistance is minus 2 into current I. The next element is 3, minus 3 into I. And the next voltage source, we are crossing plus 2 minus, that's why it is minus 5 equals to 0. Now plus 15 minus 5, it is 10, and this is minus 2 minus 3 minus 5I equals to 0, and from this you will get current, it is 10 by 5, that is 2 ampere current. Okay, so after getting this current, let us take the voltage. Now here our intention is finding not voltage, now we are calculating power across each and every element. Now the first element, here I am writing, the first element is voltage source. So voltage source, and what is the magnitude of this voltage source? 15 volts. Okay, so voltage source magnitude we know, but the power equation, now with the current also known parameter. So that's why here I am taking power equation V into I. Okay, because I know the voltage magnitude of this voltage source is 15. So 15, and the magnitude of this current is 2 ampere. Okay, so 2 ampere. So how much it is? 30 watt. The power voltage source, power delivered by this voltage source, power across this voltage source is 30 watt. And the second element is 2 ohm resistance. Second element is 2 ohm resistor. So we know the resistance value. That's why what is the power equation that I need to take? I square into R, because we know current magnitude 2. Is it right? So 2 square into resistance is 2. Okay. So 2 square 4, 4 2 is 8. So the power loss across this 2 ohm resistance is 8 watt. Right. And similarly, the third element is again the resistance 3 ohm, and I am writing power equation again I square into R. Okay. So what is the power? P equals to 2, current is 2 ampere square into 3. Is it right? Yes, resistance is 3. Now how much? 4, 3 means it is 12 watt. Okay. Now the fourth element, final element is 5 voltage source, and power at 5 voltage sources I am taking power equation V into I. It is not I square R, because I don't know the resistance of that voltage source. I know current through that voltage source is capital I, that is 2 ampere. So now the power P is V is 5 and the resistance is 2. So this is 10 watt. So this is how we have to calculate power for any electrical network. Now with this I finished Kirchhoff's voltage law with example problems, and in next class we will discuss series and parallel network. Thank you.